Welcome back to Sleepy Facts. Take a slow breath. Relax your mind. Rest smarter as we gently drift into tonight's story. If you'd like more quiet stories like this, you are welcome to subscribe. And if there is a topic you want to hear next, just whisper it in the comments. Tonight, we journey back to the very beginning, to a moment before time itself had meaning. Close your eyes and imagine nothing, not darkness, not emptiness, just nothing. No space, no time, no matter, no energy. Try to picture it, a state of non-being so complete that even the concept of emptiness doesn't apply. There was no stage on which events could unfold, no clock to measure duration, no observers to witness, just potential, pure, infinite potential. And then, in an instant too brief to measure, everything changed. 13.8 billion years ago, the universe began. Let that number settle in your mind. 13.8 billion. A number so vast it loses meaning. If you counted one number per second, without stopping, it would take you over 400 years just to count to 13 billion. And this is how many years have passed since the beginning, since the moment when nothing became everything, not with a sound, but with the sudden appearance of everything. There was no sound because there was no air to carry vibrations, no ears to hear them, only the silent unfolding of existence itself, a point smaller than the smallest thing you can imagine, smaller than an atom, smaller than a proton, smaller than a quark, infinitely small, infinitely dense, a singularity containing all the energy that would ever exist, all the matter that would ever form, every star that would ever shine, every planet that would ever orbit, every galaxy that would ever spiral through the cosmic dark, every atom in your body, every thought you've ever had, every breath you've ever taken, all of it compressed into a space tinier than a grain of sand, impossibly small, impossibly hot. Scientists call this moment the Big Bang, though it was not really a bang at all. There was no explosion into empty space, no shrapnel flying outward into a void. It was something far stranger. It was the birth of space itself, the birth of time itself, the birth of the very concepts of here and now. Before this moment, there was no before. After this moment, there was time, a canvas on which the story of everything could unfold. In the first fraction of a second, something extraordinary happened. The universe expanded faster than the speed of light. Much, much faster. This expansion is called inflation. And it happens so quickly that your mind cannot truly grasp it. In less than a trillionth of a second, in a time interval written as 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 billions of galaxies. Space itself stretched and swelled, like a balloon inflating. But imagine that balloon expanding so fast that every point on its surface would be moving away from every other point faster than light could travel between them, carrying energy with it like ripples spreading across an infinite pond. This inflation smoothed out the universe, making it remarkably uniform, almost the same in every direction, almost the same temperature everywhere, almost the same density, but not quite. There were tiny, tiny variations, quantum fluctuations frozen into the fabric of space. These tiny imperfections, smaller than 1 part in 100,000, would later become the seeds of galaxies the birthplaces of stars, the foundations of everything we see today. The temperature was unimaginable. Trillions upon trillions of degrees, hot enough that matter as we know it could not exist, hot enough that even protons and neutrons could not form. Only pure energy filled this newborn cosmos, a blazing sea of light and force, photons careening in every direction, quarks and gluons in a primordial soup. The universe was a roiling ocean of potential, waiting to cool, waiting to condense, waiting to become. As the universe expanded, it cooled, like a cup of tea left on a windowsill. Slowly, gradually, inevitably, expansion and cooling are forever linked. As space grows, the energy within it spreads out, becoming less concentrated, less intense. The temperature dropped from quadrillions of degrees to trillions, then billions. Each moment bringing the universe closer to a state where matter could exist. And as it cooled, something beautiful began. The first particles formed. Quarks emerged from the energy, tiny fundamental pieces of matter, smaller than anything that had existed before, smaller than anything we can see even with our most powerful microscopes. 6 types of quarks, each with their own unique properties. Up quarks and down quarks, strange quarks and charm quarks, top quarks and bottom quarks. They danced through the cooling cosmos, drawn together by the strong nuclear force, one of the 4 fundamental forces that govern reality, joining together in groups of 3. 3 quarks binding tightly, creating something new, forming protons and neutrons, the building blocks of atoms, the seeds of everything solid you have ever touched. Each proton composed of 2 up quarks and 1 down quark. Each neutron composed of 2 down quarks and 1 up quark, held together by gluons, particles that carry the strong force, the strongest force in nature, strong enough to overcome the electrical repulsion between positively charged protons, strong enough to bind the nucleus against all odds. 3 minutes had passed since the beginning. 3 minutes that felt like eternity. Though, of course, there was no one to feel time passing. No consciousness yet to mark the moments. Just the universe, unfolding according to the laws of physics. The universe was still incredibly hot, about 1 billion degrees Kelvin, hot as the core of the hottest stars. Still expanding, still cooling, and in those precious minutes, the first atomic nuclei formed. This process is called Big Bang nucleosynthesis, the forging of the first elements. Hydrogen nuclei formed most abundantly. Simple, elegant, pure. 1 proton standing alone, the lightest element, the most common substance in the universe. About 75% of all normal matter is hydrogen. Then came helium nuclei, slightly more complex. 2 protons and 2 neutrons, bound together by the strong force. About 25% of normal matter is helium, created in those first 3 minutes and never destroyed, still present in the universe today, in every star, in every cloud of gas, a fossil from the beginning of time. Trace amounts of lithium also appeared, the 3rd lightest element, and tiny, tiny amounts of deuterium and helium-3, isotopes that would become important later. These were the first elements, the primordial ingredients of everything to come. But that's all there was. No carbon yet, no oxygen, no nitrogen, no silicon, no iron, no gold, none of the heavier elements that make up planets or living beings. Just hydrogen and helium, floating in an ocean of light. 3 simple elements, born from the Big Bang itself. waiting billions of years for stars to forge the rest. For 380,000 years, the universe remained opaque. Think about that time span. 380,000 years. Longer than human civilization has existed. Longer than our species has walked the earth. All that time in cosmic darkness. Light could not travel freely. Photons, particles of light, were constantly scattered, bouncing endlessly between free electrons, like trying to see through a thick fog or like being inside a cloud. The cosmos glowed with a brilliant, white-hot haze. Everywhere you looked, in every direction, a uniform glow, like the inside of a light bulb. But you could not see through it. You could not see distant objects, could not see structures forming. Not yet. The temperature continued to fall, degree by degree, century by century, millennium by millennium, from billions of degrees to millions, from millions to hundreds of thousands. The cooling was relentless, inevitable, written into the mathematics of expansion. As space grew, energy diluted. As energy diluted, temperature dropped, and the universe waited for the right moment for the temperature to fall below a critical threshold. About 3,000 degrees Kelvin. Cool enough for atoms to be stable. Cool enough for electrons to settle down. Cool enough for transparency. And then a transformation. The temperature dropped to about 3,000 degrees. Cool enough for something miraculous. Electrons, which had been racing freely, slowed down. They were captured by the nuclei. Protons and electrons joined together, forming the first complete atoms. Hydrogen atoms, helium atoms, simple, stable, whole. This moment is called recombination, and with it, the fog lifted. Light could finally travel freely through space. The universe became transparent. That ancient light still travels through the cosmos today. We call it the cosmic microwave background, a faint glow now cooled to just 3 degrees above absolute zero, a whisper from the beginning of time. The universe entered what scientists call the Dark Ages, not because they were frightening, but because there were no stars yet, no galaxies, no light sources, no beacons shining in the void, just vast clouds of hydrogen and helium drifting through the darkness, cooling, expanding, waiting. The universe was patient. It had all the time in the world, all the time in existence. For hundreds of millions of years, this is how the universe remained. Dark, quiet, calm, like a deep ocean at night, like a canvas waiting for the first brushstroke. But it was not truly empty. Invisible structures were taking shape. Dark matter, mysterious and unseen, was forming vast halos, regions of space where its gravity was strongest. These halos would become the homes of galaxies, the scaffolding on which the visible universe would be built. And ordinary matter, hydrogen and helium, was slowly drifting toward these gravitational wells, falling gently through space, gathering in great clouds, swirling, condensing, preparing for transformation. The temperature continued to drop from thousands of degrees to hundreds, from hundreds to tens, eventually reaching just a few degrees above absolute zero, the coldest possible temperature, the point where motion nearly ceases. The universe had cooled dramatically from the unimaginable heat of the Big Bang to the cold darkness of intergalactic space. But within those dark clouds, within those quiet, patient accumulations of gas, the seeds of light were germinating. But within those clouds, something was happening. Gravity, patient and persistent, was at work. Tiny variations in density, Places where the gas was just slightly thicker began to pull on their surroundings, slowly at first, then faster. The denser regions attracted more gas, growing larger, denser still, pulling in everything nearby. These were the seeds of galaxies, the birthplaces of stars. About 100 million years after the Big Bang, the first stars ignited. Imagine the moment. After an eternity of darkness, after millions of centuries of cold, silent waiting, light, deep within the collapsing clouds of hydrogen, in the densest regions of the dark matter halos, gravity squeezed the gas tighter and tighter. As more gas fell inward, the pressure increased. The center grew denser, denser. The atoms moved faster, colliding more frequently. The centers grew hot, hotter, hotter than anything since the Big Bang itself. 10 million degrees, 15 million degrees, rising toward the critical threshold, until finally, at about 10 million degrees Kelvin, fusion began. Hydrogen atoms slammed together with such force that they merged, overcoming their electrical repulsion. The strong nuclear force taking hold, binding them together. 4 hydrogen atoms fusing to create 1 helium atom, and in that fusion, a tiny amount of mass was converted to energy. E equals mc squared, Einstein's famous equation. A little bit of mass becomes a tremendous amount of energy because the speed of light squared is such an enormous number, releasing tremendous energy, energy that pushed outward, balancing gravity's inward pull. The star reached equilibrium, a perfect balance between collapse and explosion, between gravity and pressure. Light burst forth, radiating into the darkness, pushing back the void. The first stars had been born, and with them, the Dark Ages ended. The universe was illuminated. These early stars were different from our sun. They were massive, brilliant, short-lived. Some contained 100 times the mass of our sun, or even more, shining with the light of millions of suns, burning blue-white hot, so bright they would blind you from light years away, containing only hydrogen and helium. No heavier elements yet existed, no carbon to form dust grains, no oxygen to create water molecules, no iron cores, just pure primordial gas. This made them unusual. Without heavier elements, they could grow extraordinarily massive, much more massive than stars today. And massive stars burn hot, very, very hot. They consumed their fuel voraciously, racing through their hydrogen in just a few million years. A cosmic blink of an eye. Our sun will burn for 10 billion years. These first stars lived less than 1% as long. Brief, brilliant lives, candles in the cosmic darkness, burning bright, burning fast. And when they exhausted their hydrogen, when the fusion in their cores began to fade, something extraordinary happened. Their cores collapsed. Without the outward pressure of fusion, gravity reasserted its dominance. The core contracted rapidly, growing hotter and denser, hot enough to fuse helium into carbon, carbon into oxygen, oxygen into neon and magnesium, layer after layer of fusion, each burning faster than the last, until finally the core was iron, quarter the speed of light, then rebounded. The core, now pure iron, collapsed in an instant, falling inward at a quarter the speed of light, then rebounded in the most violent explosion in the universe, a supernova. The outer layers exploded outward in brilliant flashes of light that briefly outshone entire galaxies. For a few weeks, a single dying star could outshine 100 billion living ones, visible across billions of light years, announcing its death to the cosmos. And in those violent deaths, in the incredible heat and pressure of the explosion, in the shock waves that rippled outward, new elements were forged, elements heavier than iron, created not by fusion, but by neutron capture, rapid processes that built up heavy nuclei, creating gold and silver, platinum and uranium, lead and thorium. All the elements necessary for planets, for geology, for chemistry, for life, for you. The calcium in your bones was made in a dying star. The iron in your blood was forged in a supernova. The gold in any jewelry you might wear was created in the final moments of a massive star's life, perhaps in a collision between two neutron stars, in a burst of gravitational waves and light. You are made of stellar debris, the ashes of ancient suns scattered across space by cosmic violence, then gathered again by gravity into new clouds, new stars, new planets, and eventually into you. The remnants of these first stars spread through space, shock waves rippling outward at thousands of kilometers per second, carrying heavy elements with them, enriching the clouds of hydrogen and helium. These enriched clouds were different. They contained the seeds of complexity, carbon atoms that could form chains and rings, oxygen atoms that could bond with hydrogen to make water, silicon atoms that could form crystals and rocks, iron atoms that could form metallic cores. New generations of stars formed from this enriched material. Population 2 stars, we call them, still mostly hydrogen and helium, but with a sprinkle of heavier elements, a dash of carbon and oxygen, a hint of iron and magnesium, enough to change everything. These stars could form planets, rocky worlds and gas giants, each generation containing more heavy elements than the last. Population 1 stars came next, stars like our Sun, rich in heavy elements, by cosmic standards at least. Still more than 98% hydrogen and helium. But that 2% makes all the difference. That 2% allows for the formation of worlds, for the chemistry of life, for the existence of beings who can contemplate their origins. Galaxies began to take shape, vast islands of stars, gas, and dust. Hundreds of billions of stars bound together by gravity, separated from other galaxies by enormous distances. Millions of light years, billions of light years, vast gulfs of nearly empty space, yet connected by gravity's invisible threads, by the cosmic web of dark matter that permeates all of space. Some galaxies formed as beautiful spirals, arms of stars spiraling outward from a bright central bulge, like cosmic pinwheels, rotating slowly, taking hundreds of millions of years to complete a single turn. Others formed as ellipticals, smooth, featureless collections of stars, oval or spherical, containing mostly older, redder stars. Still others remained irregular, chaotic collections shaped by collisions and interactions with neighboring galaxies. Our own galaxy, the Milky Way, formed about 13 billion years ago, just 800 million years after the Big Bang, growing from smaller proto-galaxies, merging and accumulating mass over billions of years. It became a beautiful barred spiral, a bright central bulge with a bar-shaped structure of stars passing through it, and elegant spiral arms curving outward, filled with young, bright stars, and the nebulae where new stars are born. Several 100 billion stars call the Milky Way home, perhaps as many as 400 billion, each one a sun in its own right. many with planets of their own. The Milky Way measures about 100,000 light-years across. Light, traveling at 300,000 kilometers per second, would take 100,000 years to cross from one side to the other. And we are located about halfway out in one of the spiral arms, the Orion Arm it's called, a minor arm, not one of the major ones, about 26,000 light-years from the galactic center, rotating around the center at about 220 kilometers per second, taking about 225 million years to complete one orbit, one cosmic year. In the entire history of Earth, our solar system has completed only 20 orbits around the galactic center. 20 cosmic years since our planet formed. The galaxy rotates slowly, patiently. Time moves differently on cosmic scales. Within the galaxies, stellar nurseries emerged, nebulae, vast clouds of gas and dust, some stretching for hundreds of light years, glowing with soft colors, red from hydrogen emission, blue from scattered starlight, dark patches where dense dust blocks the light behind. These are the wombs of stars, where new stars continue to be born. Even today, billions of years later, stars are still forming in nebulae throughout the galaxy, each star forming from a collapsing cloud, triggered perhaps by a nearby supernova, its shockwave compressing the gas, or by the passage of spiral density waves rippling through the galactic disk, each cloud's rotation causing it to flatten into a disk. Conservation of angular momentum, a fundamental law of physics. As the cloud contracts, it spins faster, like an ice skater pulling in their arms, flattening into a swirling disk. Most of the mass falling to the center, building up the protostar, growing hotter and denser until fusion ignites and a new star is born. But the disk remains, a protoplanetary disk made of gas and dust, the leftover material. And within these disks, something new appeared. Planets. It begins with dust, tiny grains of silicate and ice, smaller than particles of smoke, floating in the disk, occasionally colliding, sometimes sticking together, electrostatic forces holding them. Growing slowly, grain by grain, dust bunny by dust bunny. Over thousands of years, tiny grains became pebbles, pebbles became boulders, boulders became mountains, mountains became planetesimals, objects kilometers across, large enough that their gravity matters, beginning to pull in nearby material, growing faster now, sweeping up everything in their orbital path. The largest planetesimals became planetary embryos, objects thousands of kilometers across, moon-sized worlds competing for the remaining material. Some collided with each other, merging into larger bodies or shattering into fragments. The debris swept up by other embryos. Over millions of years, the disk cleared. The planets emerged, victors in a cosmic competition, having accumulated most of the mass in their respective orbital zones. About 9 billion years after the Big Bang, in a quiet corner of the Milky Way galaxy, a cloud of gas and dust began to collapse. Most of the material fell to the center, forming our sun, a medium-sized yellow star, stable, long-lived, perfect. Around it, in the swirling disk of remaining material, planets formed, rocky worlds close to the sun's warmth, Mercury, Venus, Earth, Mars, giant worlds farther out, where it was cooler, Jupiter, Saturn, Uranus, Neptune, composed mostly of gas and ice. 4.5 billion years ago, Earth coalesced from the disk around our young sun. Starting as a planetary embryo, growing through countless collisions with other embryos and planetesimals, each impact releasing tremendous energy, heating the growing planet, melting rock, vaporizing ice. The surface was an ocean of magma, glowing red-orange, radiating heat into space, continually renewed by new impacts. It was a violent time. The late, heavy bombardment. Asteroids and comets crashed into the inner planets, hundreds every year, thousands. Each impact adding material, each impact adding water trapped in minerals and brought by icy comets, adding the ingredients for life. Organic molecules formed in space, amino acids and sugars delivered by meteorites and comets. Even today, we find amino acids in meteorites, the same building blocks of proteins that exist in living cells. The cosmos has been doing organic chemistry for billions of years, long before life began. About 4.4 billion years ago, a Mars-sized planet called Theia struck the Earth at an oblique angle. The impact was catastrophic, vaporizing both worlds, throwing an enormous amount of debris into orbit. This debris coalesced into our moon, Earth's constant companion, stabilizing our planet's tilt, creating tides, influencing the rhythm of life to come. Slowly, the surface cooled. The impact rate decreased as the solar system cleared of debris. A thin crust formed, solid rock floating on a mantle of molten material. The first continents began to appear, small granite islands rising above the basalt ocean floor. Volcanoes erupted constantly, releasing gases from the interior, water vapor, carbon dioxide, nitrogen, sulfur dioxide, and methane. These gases formed the first atmosphere, nothing like the air we breathe today. No oxygen yet. That would come later. The atmosphere was thick with carbon dioxide, creating a strong greenhouse effect, keeping Earth warm despite the young sun being dimmer than today. Rain began to fall, not for days or weeks, but for millions of years. Torrential rains as the water vapor in the atmosphere condensed, filling the basins between continents, creating the first oceans. Dark, acidic waters colored green by dissolved iron, covering most of the planet's surface. Earth had become a water world, with small volcanic islands dotting the global ocean. Beneath those ancient seas, chemistry was at work. In the dark depths, near volcanic vents on the ocean floor, hydrothermal vents spewing superheated water rich in minerals and chemicals, creating a chemical gradient between the hot, mineral-rich vent water and the cold ocean water. Energy flowed across this gradient, driving chemical reactions. Simple molecules combined into more complex ones. Amino acids, nucleotides, lipids, the building blocks of life, forming spontaneously through natural chemical processes. No magic required, just chemistry, time, and the right conditions, protected by water from harmful radiation. The early sun emitted intense ultraviolet light that would destroy organic molecules on the surface. But deep in the ocean, in the darkness near the vents, molecules could form and persist, growing more complex, experimenting with different configurations. Most led nowhere, but some were special. Some could make copies of themselves, using the surrounding chemicals as raw materials. This is the essence of life: self-replication. The ability to make more of yourself using energy and materials from the environment. And somehow, in ways we are still trying to understand, perhaps in tidal pools, perhaps near hydrothermal vents, perhaps in bubbles of rock with minerals acting as catalysts, these molecules organize themselves into the first living cells. enclosed by lipid membranes, protected from the environment, yet able to exchange materials with it, containing genetic material, perhaps RNA at first. RNA can both store information and catalyze reactions, making it a candidate for the first genetic molecule. Later, DNA would take over the role of information storage, being more stable, better suited for long-term preservation of genetic information. Life had begun, perhaps 3.8 billion years ago, perhaps earlier. The exact moment is lost to time. The rocks that old have been metamorphosed, transformed by heat and pressure, erasing the evidence. But by 3.5 billion years ago, life definitely existed. We have fossils, stromatolites, layered structures built by photosynthetic bacteria, still forming today in a few places on Earth. Living fossils connecting us to the deep past. For billions of years, life remained simple. Single-celled organisms, bacteria and archaea, the two domains of prokaryotic life, cells without nuclei, their DNA floating freely in the cytoplasm, floating in the oceans, forming mats on rocks, living in extreme environments. Hot springs, acidic pools, deep sea vents, slowly evolving, adapting to their environment, developing new metabolisms, new ways of extracting energy from the environment. Some learn to harness sunlight, using photosynthesis to create energy, taking in carbon dioxide and water, using light energy to split water molecules, combining the hydrogen with carbon dioxide to create sugars, and as a byproduct, releasing oxygen. Free oxygen, a waste product, but one that would transform the world. At first, the oxygen reacted immediately with dissolved iron in the ocean, creating rust, iron oxide, which precipitated out, sinking to the ocean floor, forming vast deposits. The banded iron formations, layers of red iron oxide alternating with layers of other minerals found in ancient rocks around the world. Evidence of ancient photosynthesis, of life changing the planet. For hundreds of millions of years, oxygen was consumed this way, kept at very low levels. But eventually, around 2.4 billion years ago, the dissolved iron was used up. The oxygen began to accumulate in the atmosphere, slowly at first, then faster, transforming Earth forever. The Great Oxidation Event, a catastrophe for many organisms. Oxygen was toxic to most life at the time, adapted as they were to an oxygen-free world. Many species went extinct, poisoned by this reactive gas, but others adapted, learned to use oxygen to extract more energy from food. Aerobic respiration, a much more efficient process than anaerobic metabolism, releasing far more energy, making complex life possible. About 2 billion years ago, a momentous event occurred. One cell engulfed another, but did not digest it. Instead, the two formed a partnership. Symbiosis. The engulfed cell became a mitochondrion, a powerhouse of energy production, using oxygen to generate ATP, the energy currency of the cell. This was the origin of eukaryotic cells, cells with nuclei and organelles, more complex than bacteria, able to grow larger, to develop specialized structures. From these eukaryotic cells, all complex life would descend. Plants, animals, fungi, all of us carrying mitochondria in our cells, descendants of ancient bacteria working with us. A partnership billions of years old. For another billion years or more, life remained single-celled, but evolving, diversifying. Some eukaryotes engulfed photosynthetic bacteria, which became chloroplasts, the organelles that perform photosynthesis in plants. Another ancient partnership, another endosymbiosis. Life was learning to work together, to combine strengths, to create something new. About 800 million years ago, something remarkable happened. Single-celled organisms began to stick together. After dividing, they didn't separate. They remained connected, forming colonies. Some cells specialized, becoming different from their neighbors. Some for feeding, some for reproduction, some for anchoring to surfaces. Division of labor. The first multicellular organisms, at first simple and small, filaments of cells, clusters and sheets, but the potential was there for something greater. 600 million years ago, life exploded in diversity, the Cambrian explosion. Within a geologically brief period, just 20 or 30 million years, most of the major animal groups appeared. Suddenly, the oceans teemed with creatures, trilobites, with their segmented bodies and compound eyes, ancestors of insects and crustaceans. Anomalocaris, a fierce predator with grasping appendages and circular jaws. Hallucigenia, a bizarre creature with spines on its back and tentacles below. Picaia, a primitive chordate, ancestor of all vertebrates, including us. Why the sudden explosion? Perhaps oxygen levels reached a critical threshold. Perhaps an evolutionary arms race began. The development of eyes, of shells and armor, of predators and prey, each driving the evolution of the other. Or perhaps the genetic toolkit was finally in place. The Hox genes, master control genes that pattern the body, allowing for complex body plans, for segments and limbs, for heads and tails. Whatever the cause, life had crossed a threshold from simple to complex, from invisible to visible. The oceans were no longer just a green soup, but a stage for drama, for competition and cooperation, for the pageant of life. Life moved onto land, plants first, around 470 million years ago. Simple mosses and liverworts clinging to rocks near water. Later, vascular plants with roots and stems, able to transport water and nutrients, growing taller, competing for sunlight. By 360 million years ago, vast forests covered the land. Giant ferns and club mosses, towering trees, creating the first coal deposits as their remains were buried and compressed. Animals followed the plants onto land. Arthropods first, millipedes and scorpions, then vertebrates, fish with sturdy fins that could support their weight, crawling onto mudflats, hunting the arthropods, breathing air with primitive lungs. These were the first amphibians, still dependent on water for reproduction, laying eggs in ponds and streams, but exploring the land, finding new opportunities, new food sources, new habitats. Their descendants became reptiles around 320 million years ago, evolving the amniotic egg, an egg with a hard shell and membranes to protect the embryo. No longer tied to water, able to reproduce on land. This freed them to spread into deserts and mountains, into every terrestrial habitat. Reptiles diversified dramatically. Some became the ancestors of mammals. Others became dinosaurs. Dinosaurs ruled for 160 million years, from about 230 million years ago to 66 million years ago. Longer than mammals have existed, far longer than humans. They adapted to every environment. Tiny feathered creatures, massive long-necked sauropods, fierce predators like Tyrannosaurus, armored herbivores like Stegosaurus and Triceratops. Flying pterosaurs soared through the skies. Marine reptiles swam in the oceans. The Mesozoic era was their time, the age of reptiles, until an asteroid struck 66 million years ago. An object about 10 kilometers across, traveling at tens of thousands of kilometers per hour, struck the Yucatan Peninsula. The impact was unimaginable, creating a crater 180 kilometers wide, releasing energy equivalent to billions of nuclear weapons, vaporizing rock, creating an earthquake that shook the entire planet, triggering tsunamis that swept across the oceans, throwing trillions of tons of debris into the atmosphere, blocking the sun. Temperatures plummeted, photosynthesis ceased, food chains collapsed. 75% of all species went extinct, including all non-avian dinosaurs, ending their reign, opening space for new creatures. Mammals had existed since the dinosaurs' time, small, mostly nocturnal, hiding in burrows, feeding on insects and plants, limited by the dominance of reptiles. But with the dinosaurs gone, mammals diversified, rapidly filling the vacant niches. Some grew large, others developed specialized diets: grazers, browsers, predators, burrowers, climbers, swimmers. Primates appeared early, small tree-dwelling creatures with grasping hands and forward-facing eyes, adapted for life in the canopy, for judging distances, for leaping between branches. These traits would serve their descendants well in ways they could never anticipate. 200,000 years ago in Africa, in the grasslands and forests of East Africa, our own species appeared. Homo sapiens, anatomically modern humans. But we were not the first humans. Our genus, Homo, had existed for over 2 million years. Homo habilis, the toolmaker. Homo erectus, who mastered fire and migrated across continents. Neanderthals and Denisovans, our cousins, with whom we coexisted and even interbred. But Homo sapiens was different. We had larger brains, more gracile bodies, and something else, something harder to quantify. A capacity for symbolic thought, for language, for art and culture, for imagining what is not. We looked up at the night sky with wondering eyes, those same stars that had shone for billions of years, now beheld by conscious minds. We saw patterns in the stars, connected them into constellations, told stories about them, created myths to explain their movements. The sun became a god, the moon a goddess, the planets wanderers with divine significance. We asked questions, the same questions you might ask, the same questions that echo through the ages. Where did we come from? Why are we here? What is our place in this vast cosmos? What happens when we die? Is there meaning to existence? Are we alone? For most of our history, we did not know. We could not know. The tools did not exist. The framework did not exist. The scientific method had not been invented. So we created myths and legends to explain the world. Beautiful stories, meaningful narratives connecting us to the land, to our ancestors, to the cosmos. Every culture developed its own creation story, its own explanation for the stars. The Babylonians tracked the planets meticulously, seeing omens in their movements. The ancient Greeks wondered if the stars were other suns, if worlds existed beyond our own. Chinese astronomers recorded comets and supernovae for thousands of years, creating a historical record that modern scientists still use today. Indigenous peoples around the world developed sophisticated astronomical knowledge, tracking the seasons, predicting eclipses, using the stars for navigation, for agriculture, for ritual and ceremony. We were curious, we observed, we sought patterns, but we never stopped asking, never stopped searching. And slowly, gradually, over centuries and millennia, we developed new ways of knowing. Mathematics, a language for describing patterns, for making predictions, for understanding relationships between quantities and shapes. Philosophy, systematic thinking about existence, about knowledge, about ethics and meaning. And eventually, science, a method for testing ideas, for distinguishing truth from falsehood, for building a reliable picture of reality, based not on authority, but on evidence, not on tradition, but on experimentation, not on what we wish to be true, but on what is actually true. Only in the last century have we begun to understand our true story, the story of the universe itself. In 1929, Edwin Hubble made a discovery using the largest telescope in the world at the time, the 100-inch telescope on Mount Wilson. He measured the light from distant galaxies and found something astonishing. Their light was shifted toward the red end of the spectrum. Redshift, the same effect that makes a siren sound lower as it moves away from you. The Doppler effect. Galaxies are moving away from us, all of them in every direction. And the more distant the galaxy, the faster it recedes. The universe is expanding, growing larger every moment. Every second, space itself stretches, carrying galaxies apart. If it is expanding now, Hubble realized, it must have been smaller in the past. Wind back the clock far enough, and everything converges to a single point, the Big Bang, a beginning to time and space. This was revolutionary. Many scientists resisted the idea, preferring an eternal, unchanging universe. But the evidence mounted. In 1965, two scientists working for Bell Labs, Arno Penzias and Robert Wilson, were testing a sensitive radio antenna. They kept detecting a persistent noise, a hiss of static coming from all directions. They checked everything, cleaned pigeon droppings from the antenna, eliminated every source of interference they could think of. But the noise remained, uniform, constant, everywhere. They consulted with theoretical physicists who told them what they had found: the cosmic microwave background, the afterglow of the Big Bang, predicted decades earlier but never observed until now. Light from 380,000 years after the beginning, now cooled to just 2.7 degrees above absolute zero, stretched by the expansion of the universe from visible light to microwaves. But still there, still detectable, a whisper from the beginning of time, exactly as predicted by theory. Proof that the universe had a beginning, proof that it was once incredibly hot and dense, proof that the Big Bang really happened. For this discovery, Penzias and Wilson won the Nobel Prize. In the decades since, we have measured its age with remarkable precision, 13.8 billion years, using multiple independent methods, all agreeing. The cosmic microwave background, the ages of the oldest stars, the rate of expansion, the abundance of elements, all pointing to the same conclusion. A universe with a finite age, a cosmic story with a definite beginning. We have mapped the distribution of galaxies across billions of light years, creating three-dimensional maps of the cosmos, seeing the large-scale structure, the cosmic web, filaments of galaxies stretching across hundreds of millions of light years, separated by vast voids, nearly empty regions where few galaxies exist. The pattern predicted by our theories of dark matter and structure formation. We have discovered that ordinary matter, the stuff we can see and touch, makes up only 5% of the universe. 5%. Everything you've ever seen, every star, every galaxy, every planet and person, all the light in the cosmos is just a tiny fraction of what exists. About 27% is dark matter, matter that doesn't emit light, that doesn't interact with electromagnetic radiation, but whose gravity we can detect, holding galaxies together, forming the scaffolding of the cosmic web. We don't know what it is. Perhaps exotic particles not yet discovered in our laboratories. Perhaps something stranger still. And the remaining 68% is dark energy, even more mysterious. A property of space itself, causing the expansion to accelerate, pushing galaxies apart faster and faster. We discovered this in the late 1990s by studying distant supernovae, and it shocked the scientific community. We expected the expansion to slow down, pulled back by gravity, but instead it's speeding up, driven by some unknown force, some property of the vacuum. We call it dark energy, but we don't understand it. It's one of the deepest mysteries in physics. We have sent telescopes into space, above the blurring effects of Earth's atmosphere. The Hubble Space Telescope, launched in 1990, showing us the universe in unprecedented detail. Deep field images pointing at apparently empty patches of sky and finding thousands of galaxies, each containing billions of stars in a region of sky smaller than a grain of sand held at arm's length. Multiply that by the entire sky, and there are hundreds of billions of galaxies, perhaps 2 trillion, each a universe unto itself. The James Webb Space Telescope, launched in 2021, peering even deeper using infrared light. Seeing the first galaxies form just a few 100 million years after the Big Bang. Witnessing cosmic dawn when the first stars ignited. The Chandra X-ray Observatory, seeing the high-energy universe, black holes and neutron stars, supernovae and galaxy clusters, events so violent and hot they shine in X-rays, peering deeper into the universe than ever before, seeing galaxies as they were billions of years ago. Because light takes time to travel, looking out in space is looking back in time. When we see a galaxy 10 billion light-years away, we see it as it was 10 billion years ago, when the universe was younger, when stars were forming more rapidly, when galaxies were smaller and more chaotic. We are cosmic archaeologists, digging through time, reconstructing the history of the universe from the evidence that reaches us. We have detected gravitational waves, ripples in space-time itself, predicted by Einstein in 1916, but not detected until 2015. Using instruments called LIGO and Virgo, laser interferometers sensitive enough to measure a change in distance smaller than the width of a proton, caused by gravitational waves from colliding black holes billions of light-years away. 2 black holes, each dozens of times the mass of the Sun, spiraling together, orbiting faster and faster, radiating energy as gravitational waves, until finally merging in a fraction of a second, releasing more energy than all the stars in the observable universe combined. We detected the ripples, a chirp in the data, a signal that matched predictions exactly, confirming Einstein's theory a century after he proposed it. Since then, we've detected dozens more, colliding black holes, colliding neutron stars, events that shake the fabric of space-time, giving us a new way to observe the cosmos, not with light, but with gravity itself. We have found thousands of planets orbiting other stars, exoplanets, using various detection methods. The transit method, watching for the tiny dimming as a planet passes in front of its star. The radial velocity method, detecting the wobble as a planet's gravity tugs on its star. We found hot Jupiters, giant planets orbiting close to their stars, scorched and tidally locked. Super-Earths, rocky planets larger than Earth. Planets orbiting in the habitable zone, the region where liquid water could exist. Some similar to Earth in size and temperature. Some utterly alien. Planets with two suns, rogue planets drifting through interstellar space, planets made of diamond, planets with surfaces of molten lava, water worlds covered entirely by deep oceans. The diversity is staggering. Our solar system is just one example among countless variations, raising the profound possibility that we are not alone. If planets are common, and the building blocks of life are common, and we know they are, we find them in space, then perhaps life is common too. Perhaps it arises wherever conditions allow. We don't know yet. We're searching, listening for radio signals, analyzing the atmospheres of distant planets, looking for biosignatures, oxygen, methane, combinations of gases that suggest biological activity. We haven't found definitive evidence yet, but the search continues, and the universe is vast, full of possibilities. And yet, for all we have learned, mysteries remain, deep mysteries, questions that keep cosmologists awake at night, that drive decades of research, that may reshape our understanding. What came before the Big Bang? If time began with the Big Bang, can we even ask what came before? Or is before a meaningless concept without time? Some theories suggest a multiverse, an infinite collection of universes, each with different properties, different laws of physics. Our universe just one bubble in an eternal cosmic foam. Others propose a cyclic universe, expanding and contracting. Big Bang followed by Big Crunch, followed by another Big Bang, an eternal cycle with no true beginning. Still others suggest our universe arose from quantum fluctuations, a random occurrence in a quantum realm where universes spontaneously appear and disappear. We don't know. Perhaps we can never know. Perhaps some questions lie forever beyond science. But we keep asking, what is dark matter made of? We know it exists. We can map its distribution by its gravitational effects on galaxies and galaxy clusters on the cosmic microwave background. But we cannot detect it directly. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic forces, only gravity. Candidates abound. WIMPs, weakly interacting massive particles, exotic particles predicted by supersymmetry, axions, ultralight particles proposed to solve other problems in physics, primordial black holes formed in the early universe, sterile neutrinos, or something else entirely, something we haven't imagined yet. Experiments run deep underground, shielded from cosmic rays, waiting for a dark matter particle to collide with a detector atom. So far, nothing. The search continues. What is dark energy? Why is the expansion accelerating? Is it truly a property of empty space? A cosmological constant, as Einstein once proposed, then rejected, then was proven right after all? Or is it something dynamic, changing over time? Quintessence, some call it, a field permeating space. Or perhaps our theory of gravity is wrong on cosmic scales. Perhaps general relativity needs modification to explain what we see. We don't know. It's the biggest mystery in cosmology, constituting most of the universe, yet completely unknown to us. Why does the universe have the properties it has? Why is the speed of light exactly what it is? Why is the strength of gravity just right to allow stars to form? Why is the strong nuclear force strong enough to bind nuclei, but not so strong that protons fuse too easily? Why are the masses of particles the values they are? Change any of these constants by a small amount, and the universe would be radically different. Stars might not form, or they might burn out instantly. Atoms might not be stable. Chemistry might not be possible. Life would be impossible. This is called fine-tuning, and it's deeply puzzling. Is it just luck? Are we in the one universe out of countless possibilities that happens to allow life? The anthropic principle suggests we can only observe a universe that allows observers to exist. So it's not surprising that we find ourselves in such a universe. But it doesn't explain why this universe exists, or whether others do too. Is our universe the only one? Or are there others beyond our reach? Parallel realities with different laws of physics, different values for the fundamental constants, different outcomes to quantum events. The multiverse hypothesis, suggested by some interpretations of quantum mechanics and by some versions of inflation theory, predicts an infinite number of universes. In most, conditions are not right for life. In some, perhaps they are. And maybe, in some, there are beings asking the same questions, looking up at their own night sky, wondering if they are alone. These questions keep scientists awake at night, searching, calculating, dreaming, building experiments, developing new theories, testing predictions, slowly, incrementally, pushing back the boundaries of knowledge, each answer raising new questions, each discovery revealing new mysteries. That's the nature of science, not a finished product, but an ongoing process, an endless frontier. And in some ways, the questions are as beautiful as the answers, because they remind us how much we have yet to learn, how vast and strange the cosmos is, how privileged we are to be able to ask. But tonight, as you drift towards sleep, as your breathing slows, as your mind quiets, consider this. You are made of stardust, not metaphorically, not poetically, literally. Every atom in your body, except for hydrogen, was forged in the heart of a dying star, or in the violent collision of stellar remnants. The calcium in your bones that gives them structure and strength was created when a massive star fused silicon and oxygen in its final days. The iron in your blood that carries oxygen to your cells, that gives blood its red color, was created in the last moments before a supernova, when the core of a star collapsed, creating the heaviest elements through rapid nuclear reactions. The carbon in your cells that forms the backbone of every organic molecule was made when helium atoms fused together in the cores of red giant stars. The oxygen you breathe was created when carbon and helium fused in stars slightly more massive than the sun. The nitrogen in your DNA, the phosphorus in your ATP, the sulfur in your proteins, all of it created billions of years ago in stellar furnaces scattered across the galaxy. You are made of stellar debris, recycled star stuff, the ashes of ancient suns, scattered across space by cosmic violence, supernovae and stellar winds, planetary nebula and neutron star collisions. then gathered again by gravity into new clouds, new stars, new planets, and eventually into you. The atoms in your left hand may have come from different stars than the atoms in your right hand. You are a collection of material from countless sources, brought together by chance, organized by chemistry and biology into a conscious being, a pattern that can think and feel. You are the universe experiencing itself. This is not hyperbole. You are literally made of the universe. The same atoms that were once in stars are now in you, arranged in such a way that they have become aware. Conscious matter, contemplating its own existence. Think about that for a moment. Atoms themselves are not conscious. A carbon atom knows nothing, feels nothing, but arrange enough atoms in the right way, connect them into molecules, organize those molecules into cells, connect those cells into a nervous system, and something emerges. Something greater than the sum of its parts. Awareness, consciousness, the ability to know that you exist, to wonder about your place in the cosmos, to feel awe and wonder, to appreciate beauty, to love and be loved, to create and imagine. All of this emerges from matter, from the same atoms that make up rocks and stars, but organized in a special way. A way that allows the universe to become aware of itself. You are stardust that learned to think, atoms that became conscious. The universe looking back at itself with your own eyes. When you look up at the stars, you are the universe observing itself, admiring its own beauty, contemplating its own nature. There is no separation between you and the cosmos. You are not in the universe. The universe is not out there, separate from you. You are the universe, a temporary pattern, a wave in an ocean, made of the same water, just moving through it for a brief moment. From nothing came everything. From energy came matter. From matter came stars. From stars came planets. From planets came life. From life came consciousness. From consciousness came wonder. An unbroken chain stretching back 13.8 billion years, connecting you to the very beginning. You are not separate from the cosmos. You are a part of it. A way for the universe to know itself. The story continues. Even now, the universe expands. Galaxies drift farther apart. Stars are born and die. Planets form and evolve. Life emerges and adapts. And somewhere, perhaps on countless worlds, other beings look up at their night sky, asking the same questions we ask, feeling the same wonder we feel. Billions of years from now, our sun will exhaust its hydrogen fuel. It will swell into a red giant, engulfing Mercury and Venus, perhaps Earth as well. Then it will shed its outer layers, creating a beautiful planetary nebula. Its core will collapse into a white dwarf, slowly cooling over trillions of years, eventually becoming a black dwarf, a dark, dense ember, a monument to what once was. But the universe will continue. New stars will form from the remnants. New planets will coalesce. New stories will unfold. The universe is patient. It has time. All the time in the world. All the time in the cosmos. And you, here now, in this moment, are part of that story. Your life, however brief on cosmic scales, matters. Your thoughts, your dreams, your experiences are the universe becoming aware of itself, appreciating its own beauty, finding meaning in the vast expanse. So rest now. Let your breathing slow. Feel yourself connected to everything, to the earth beneath you, formed from ancient stardust, to the air around you, exhaled by ancient plants, to the stars above you, birthplaces of the elements that make you possible. You are home. You have always been home. You are exactly where you belong. In this universe, at this time, in this moment. The atoms in your body have traveled far, through space and time, through stars and planets, through countless transformations, to be here now as you. And when your time ends, those atoms will continue, becoming part of the earth, the air, the sea, perhaps one day, part of new life. You are temporary, but you are also eternal, a pattern in the flow of matter and energy that has always existed and always will, just in different forms. There is no rush. The universe has been unfolding for 13.8 billion years. It will continue for trillions more. Your rest is a part of that unfolding. Your dreams are cosmic. Your sleep is sacred. As you close your eyes tonight, you join the rhythm of the cosmos, the turning of planets, the burning of stars, the expansion of space itself, all of it moving together in a dance that began at the beginning of time. From the first moment to this moment, an unbroken thread connects everything. The Big Bang still echoes through the universe, in the cosmic microwave background, in the expansion of space, in the stars that still shine, in the life that still flourishes. In you. You are the universe's way of remembering its own beginning, of celebrating its own existence, of finding beauty in the pattern. Let that thought comfort you. You are not alone. You are connected to everything that has ever been and everything that will ever be. The boundary between you and the universe is thinner than you think. You are not in the universe. You are the universe, experiencing itself from a particular point of view for a particular period of time. And that is extraordinary. As you drift into sleep, imagine yourself floating through space, past the moon, past Mars and Jupiter, out beyond the edge of our solar system, into the vast space between stars. You are safe. You are calm. The stars surround you like distant lanterns, each one a sun, each one a story, some with planets of their own, some dying in spectacular explosions, some being born in clouds of gas and dust. All of them part of the same cosmic family. Float past our galaxy, see it from outside, a beautiful spiral of light, hundreds of billions of stars rotating slowly, held together by gravity. Our sun is just one star among many, a tiny point of light in one of the spiral arms. And yet, it is our home, the center of our story, the reason we exist. Pull back further, see the universe on the grandest scale, clusters of galaxies, superclusters, vast filaments of light separated by enormous voids, the cosmic web, a pattern of structure spanning billions of light years. All of it grown from tiny fluctuations in the early universe, quantum ripples amplified by time and gravity into the majestic architecture you see now. And yet, with all this vastness, all this complexity, all this beauty, the most remarkable thing is awareness itself. The fact that matter can organize itself into patterns that think, that feel, that dream, that look back at the universe and understand it. You are one of those patterns, and that makes you precious, irreplaceable, a unique perspective on existence that has never occurred before and will never occur again in quite the same way. Rest in that knowledge. You have earned your place in this cosmos simply by existing, simply by being aware, simply by caring. The universe gave rise to stars. Stars gave rise to planets. Planets gave rise to life. Life gave rise to consciousness, and consciousness gives rise to meaning. You are the universe creating meaning from itself, finding purpose in the pattern, discovering beauty in the mathematics, experiencing love, joy, wonder, none of which are separate from the cosmos, all of which are the cosmos itself, feeling, thinking, being. Tomorrow, when you wake, the universe will still be here, still expanding, still evolving, still creating, and you will be part of it. Your thoughts will ripple through space. Your actions will shape the future. In small ways, perhaps, but every small way matters. Every choice, every kindness, every moment of wonder adds to the story of the universe. For now, though, rest. Let your mind settle like dust after a storm. Let your thoughts fade like stars at dawn. Let your breathing slow like the cooling of the early universe. You are safe. You are held by gravity, by the earth, by time itself. Nothing is required of you right now except to be, to exist, to rest. The universe waited 13.8 billion years for you. It can wait a few more hours while you sleep. The stars will still be there in the morning. The galaxies will still spiral. The cosmos will still expand. And you will still be part of it, connected, woven into the fabric, a thread in the tapestry, a note in the symphony, a word in the story. So sleep now, deep and peaceful, knowing that you are exactly where you should be, when you should be here. Part of something vast and beautiful, something that began before time and will continue beyond comprehension. You are stardust. You are the universe. You are home. Thank you for listening with Sleepy Facts. Let your breath steady. Let your thoughts grow quiet. Rest smarter by allowing your mind to settle into the rhythm of night. If you enjoyed this moment of calm, you are welcome to subscribe. And if there is a topic you want to hear next, simply leave it in the comments. Wishing you a peaceful night and gentle dreams.